Hello and welcome back to the MoDyPy Basics tutorial series. My name is Ralf and in this tutorial I will show you how to model a bouncing ball. If you are the kind of person who rather reads tutorials instead of watching them, hop over to docs.modypy.org where you will find this tutorial series in text form. In this tutorial, we will look at zero-crossing events, and we will use them to model the bouncing of a simple ball. So the idea is that we have a ball with a given mass, and that ball is accelerated towards the ground. And we have a state, which is the height relative to the ground, and another state, which is the velocity relative to the ground. And we want to detect when the ball hits the ground and then use the laws of reflection here to have the ball bounce back with reduced energy so that we get this kind of graph where the ball is always hitting the ground once again and then going back up and so on until it loses its energy. And the first thing that we'll do is we will model the falling ball. And that is a relatively simple model. We have two states, the height and the velocity, and we know that the derivative of height is the velocity and the derivative of the velocity is simply the gravitational acceleration minus g. And if we simulate that system, we will just see that the ball keeps falling and falling and falling, accelerating all the time, but it doesn't bounce back when it reaches height 0. Why would it? We didn't model it that way. What we want to do is to have it bounce back. So we need to detect whenever it hits the ground, and then we need to change the velocity so that it's pointing upwards again. So let's look into how we do that in the code. Here I already modeled the falling ball. So I imported the relevant definitions. We need a system, we need a state, and we need something for simulation, and we need something to plot the result. And we have some constants here. We have the gravitational acceleration, so we're working in the SI system, and we have the initial velocity and the initial height in meters. And here we have our two states, the height and the velocity. And the derivative of height is the velocity, and the derivative of velocity is this function which simply returns negative g as a constant. And I did simulate that already up till 2 seconds and plotted the result. And if we look into that, we see that the ball is simply falling through the ground as we've seen it previously in the slides. In order to change that, we need to detect a zero-crossing event. For that, we use a zero-cross event source, and we declare that here. We call it the ground event, zero-cross event source. The zero-cross event source is also part of the system. And we need an event function. And the significance of that event function is that it accepts a system state and must return a scalar or a vector of scalars indicating the occurrence of the event. And the event is set to occur when this value that is returned there becomes 0. So what could be a good event function for us? We want the event to happen whenever the ball hits the ground. And that is the case when the height becomes 0. And as we know, our states are essentially callables that accept a system state and return a value or a series of values. So they conform to the protocol that we require for the event function. So we can specify the height as event function directly. Now we are not interested in when the ball crosses the 0 layer from the negative towards the positive. We are only interested when the ball comes from above and goes below the 0 height. So we specify the direction here, and that direction is -1, indicating that the derivative of our event function at the 0 needs to be negative. So it needs to be crossing from the positive to the negative direction. Now we need something to handle that event, and that is an event handler. That is a simple function that again accepts a system state. So we call that bounce back. We accept the system state. Now we want to change the velocity of in the system state by changing its sign. And to do that, we use the velocity state and call its setValue method. And that requires us to pass a system state, which we want to change, and the new value. And the new value is simply the old value of the velocity with inverted sign. So we write minus velocity of system state. And that's it already. The point here I have to specify that it's the value. Yeah. So that's it already for the definition of the event handler. Now we need to register that event handler. And we do that by calling the register listener function on the ground event object and simply give it the bounce back function. So whenever this ground event is triggered, the bounce back function will be called. Now let's try this again. We would expect the ball to bounce back now instead of going through the ground. And here we see the ball is falling and it's approaching the ground, and once it hits the ground, it reverses direction. In addition to reverse the direction, we would like to it to lose some energy. So we define a constant of restitution here, which is lower than 1, and multiply it in here. So we have a lower velocity going away from the bounce than going into the bounce. And we can run this for a little bit longer to see whether it works even with multiple hits. And we see that it hits the ground, bounces back. The final height is a little bit lower than the height that we let it fall from. We see that it's bouncing back multiple times and always losing energy. And here in the end, we can already see, when we zoom in, that we are nearing the accuracy of the integration step size. Now you may have thought, why did he specify 8 seconds there? We always did it for 10 seconds. That seems arbitrary. There is a reason for that. And to show you, let me extend the time to 10 seconds and run the simulation again. And what happens, it will take some time and then fail with an excessive event error. And the reason for that is that the ball loses more and more energy. And you can see that the times between consecutive impacts gets lower and lower. Here we have about 2 seconds, and here it's already only about 0.7 seconds. And it's getting less and less. And at some point, we will have multiple impacts per integration step. So time will not advance anymore, really. You will have one integration step. You will see that there is an impact there. You will step back towards that impact and continue simulating from there. And as soon as there are 1,000 such events consecutively without having any integration step, without any event, the simulator will raise this exception. It will simply give up. This kind of behavior is called Zeno behavior, after the Greek philosopher Zeno of Elea. Zeno of Elea theoretized about infinite problems, such as the race of the tortoise and the hare. And while we know that many of his problems are solvable today, this kind of problem still remains mostly unsolved regarding simulation. There are many approaches to handling it, but in most cases, the simulators simply fall back to just aborting simulation. So that's it for this tutorial. There's still a lot in store for you. So I hope to see you back soon. Bye bye.